All right. Hey, everybody. So in this video, we get to introduce one of the big concepts from calculus, which we will now explore with a more refined real analysis point of view. We are talking, of course, about the derivative. So I want to start with the standard definition of the derivative. This is the same, maybe the language is a little more technical, but it's the same definition that you would have seen in Calculus 1. So we're taking a function that is defined on a domain D, and we're going to focus on a specific point, P, that is both an element of the domain and also an accumulation point of the domain. Right, so not only can we plug P into the function f, but we can, it's an accumulation point, so there are nearby points in the domain that we can also plug into the function f. Then f is said to be differentiable at the point P if and only if this limit exists, and that's equivalent to this limit down here existing. So a few words about this overall. First of all, let me draw some axes here. The sort of intuition that we have, boop, here we go. The intuition that we typically have from Calculus 1 continues to hold true. So our function, maybe it looks like this. I'm just sort of graphing it like this. But let's pretend that our domain is a connected subset of the real numbers. Let's focus on a point. Maybe this is P. And then this up here is f of P. Then I can create a limit in the following two ways, right? Either by taking x values that are nearby, and I'll sort of denote that maybe here in purple. So I could take an x value that's nearby. So here's a corresponding point x, and its corresponding height f of x. Or I could think of this in a slightly different language by introducing this letter h, and not considering x as a point x, but considering it as the point P plus h, right? So h is that distance, and then I can write x as P plus h, and then this would become f of P plus h. So by that translation, right, the translation of x equals P plus h, I can translate between this notation up here and this notation down here. So what do these represent? Well, as we've seen in calculus, this represents a difference quotient between the heights of our function, right? So f of x minus f of p is going to be that distance right there. And then x minus p is going to be this distance right here. And so I'm going to take that distance divided by this distance to get the difference quotient, aka the slope of this line that is connecting these 2 points together, right? So I could get the slope of that line connecting the 2 points, which is the same thing as the slope of, I drew that kind of poorly, but the slope of the line that's connecting these points here, right? I'll just sort of draw it like that. So we can calculate the slope of that line, and that would be a quantity that we can calculate for any given x and any given, well, I guess for our fixed p-value, aka for any given h value. So we calculate that, and then we take a limit of these expressions as x goes to p or as h goes to 0, and what we'll get are points that are closer and closer and closer to p, and we'll calculate this difference quotient between 2 points that are getting closer and closer and closer. And if that limit exists, it will represent, sort of the physical quantity of the instantaneous rate of change of the function f, or what we know as the derivative. Now, worth pointing out, right? So that's sort of our Calc 1 understanding, and that completely holds true here. It is worth pointing out that we also have our real analysis understanding of what it means to calculate this limit, right? Or what it means to calculate this limit. And so I'm going to erase what we have up here, just as far as this picture. And I just want to briefly talk about this in sort of the abstract real analysis framework. Specifically, if I want to focus on this, I could really focus on either of them, I guess. But if I want to focus on let's say the first one. If I want to focus on this first one, because our p-value is fixed, right? P is just a fixed constant. The quantity f of x minus f of p over x minus p, for a fixed p-value, this quantity is a function of x, right? I plug in an x value and I get a given, quantity out of there. This is a function of x, and it is not defined at p, but it is defined at all of our other x values that I'm allowed to plug into the function, right? It's not defined at p because I would end up dividing by 0, but it is defined at other x values. So that in and of itself is a function of x defined on the takeaway, the point p. All right, so p is not in the domain of this expression, but it is still an accumulation point of the domain of this expression because it was an accumulation point of d. So because p is an accumulation point of this new domain for this new function, I can explicitly talk about taking a limit as my x values in the domain approach the point p. And so finally, what we of course mean by this is that hidden within all of this is an epsilon delta expression, right? So very, very formally, what this means is, what this means is that for all epsilon, there exists a delta such that if our x values satisfy x minus p is less than delta, then our output values, right? And our output values here are this quantity. So that quantity minus the limit will be less than epsilon. And let me write that up quickly. So we would have that quantity, f of x minus f of p over x minus p minus the given limit is less than epsilon. And so now it's worth actually giving this object a name. It's the name that you recognize. If this limit exists, we will call the limit the derivative of the function at the point p, and we will denote it with the notation f prime of p. And so when we say that these limits exist, we're saying that they equal f prime of p, whatever that number is. And that really means that under the hood, there is an epsilon delta definition happening here. Oftentimes, we have proven, or maybe I should say this, we have proven a lot about limits of functions. And so oftentimes we can refer to those limit results, right? And this would have been back in maybe chapter 6, chapter 7, I think chapter 7, we can refer back to those limits about, or those results about limits of functions. Just in this case, the function that we're talking about is this function here, and that will give us corresponding results about derivatives, which we'll see in a future video. So that is our introduction to the derivative. In videos to come, we will see how we can play around with this and derive a lot of the rules that we know and love and learned in Calc 1. So I'll see you in the next video.